the last time you looked into the hollow bowl of a shiny stainless steel serving spoon? If you hold it far enough away, you see a clear reflection of your own face, completely upside down. But if you flip that spoon over and look at the bulging back, the reflection immediately snaps upright and your face looks tiny. This simple piece of kitchenware behaves exactly like a scientific optical tool. By curving a reflective surface, we force light to change paths, creating inverted, shrunken, or magnified versions of reality. Geometrically, a curved mirror is simply a specific slice taken from a larger, hollow sphere of glass. To map how light interacts with this curve, we identify three main points. The exact center of the mirror's surface is the pole. The original center of that imaginary glass sphere is the center of curvature. The straight line cutting directly through both points is the principal axis. Exactly halfway between the pole and the center of curvature sits the principal focus. Because it is perfectly in the middle, the radius of curvature is always exactly twice the focal length. To map exactly how light reflects off this surface, you don't need complex mirror formulas. You only need a ruler, a pencil, and three simple rules for drawing baseline light trajectories. By mastering the geometry of these simple lines through scale drawing, we can predict exactly where light will go and what kind of image it will form. This is a photograph of a crowded street in Kampala. Navigating this high-density mix of heavy vans and fast-moving bodabodas requires drivers to have a massive field of view to survive the road. We will use this bodaboda rider in the red helmet as our specific object to see how optical physics solves this driving problem. We place the rider on the left side of our ray diagram. On the right, we place a convex driving mirror, which curves outwards toward the street. We draw our first ray from the top of the rider, traveling parallel to the principal axis. Because the mirror bulges outward, the light hits the curve and diverges, bouncing sharply away from the center line. The challenge here is that the focus and center of curvature are physically trapped behind the mirror, where real light cannot go. So we draw a dashed virtual line backward from that diverging ray, aiming straight for the focus point. Next, we draw a second incoming ray aiming directly at the center of curvature. It hits the mirror at a perfect right angle and reflects straight back on itself. Extending its virtual dashed line behind the glass creates an exact point of intersection. Because this intersection relies entirely on virtual rays crossing behind the mirror, a convex surface always creates an image that is virtual, perfectly upright, and diminished. Shrinking the physical world into a smaller reflection is exactly how it compresses a busy street to give a rider a wider, life-saving field of view. Now we flip to the inverse tool, the concave mirror, which curves inward like a hollow cave. Because of its shape, it behaves entirely differently. When parallel light rays enter this curve, they don't bounce away. The inward slope captures the rays and forces them all to converge. They physically intersect in the real world, exactly at the principal focus. Capturing and crossing real light rays means you capture their physical heat. Rural communities use large concave mirrors as solar cookers because they can gather scattered sunlight and focus it into a single intense point, hot enough to boil water. With a concave mirror, the resulting image completely changes depending on how close the object is to the surface. Let's test your ability to predict this outcome using scale drawing. Here is the setup. You have a concave mirror. Mark your principal focus at 3 centimeters and your center of curvature at 6 centimeters. Place an object that is 2 centimeters tall, exactly 8 centimeters away from the mirror. Pause the video right here. Grab a piece of graph paper and a ruler and draw your 2 standard rays to determine the precise location and nature of the image. Let's draw the solution together. We start with our principal axis, marking F at 3 centimeters and C at 6 centimeters. Then we place our 2 centimeter tall object directly on the 8 centimeter mark. We trace our first standard ray parallel to the axis. It hits the inward curve and reflects straight down through the focus. Notice that we apply bold directional arrows to our light rays, so the direction of travel is clear. Next, we trace the second ray straight through the principal focus. It hits the mirror and reflects exactly parallel to the axis. The exact spot where these 2 reflected lines cross gives us the top of our image. Because the actual light rays crossed in front of the mirror, the image is physically there. It is a real image. Looking closely at our drawn arrow, we can confidently state that the image is inverted, and diminished. Let's lock in these rules by comparing the two shapes side by side. Concave mirrors converge light. They form different types of images based on where the object sits. By concentrating energy, they power tools like solar cookers and dentist mirrors. Convex mirrors diverge light. They will consistently produce an image that is virtual, erect, and diminished. This guaranteed shrinking effect expands the field of view, securing roads for bodas and corners for supermarkets. And remember this critical rule for your final exams. An accurate drawing without directional arrows on the light rays will lose marks. By understanding the geometric paths of light, we take a shiny piece of glass and manipulate it to do exactly what we need. We turn a curved surface into an engine for boiling water, or a lens that protects us in heavy traffic.